I'm going to present a part of a project that has been going on for some time. This is about buckling and fracture of thin foils. We who did this are Pastole, myself, and Martje Shahmardani and Sharon Kao-Walter. The motivation for the present study is a series of experiments that were done a couple of years ago on laminates made of polymer foils together with aluminium foils. And that is what you see in the picture to the left, and you see that it wrinkles, buckles during the experiment. There's a metallic sheet that you see, and there is a horizontal crack in the middle. The reason for the interest of these laminates is what you see to the right. You can see tensile tests made of with this freestanding aluminium. See, that's the peak you see to the lower left-hand side of the graph. And then you see the polymer that is stretching, and the load that it carries is increasing, but the peak of the load disappears far to the right of this graph. So at these low small strains, it isn't carrying much load. But when you add these two layers together, you get the laminate curve, and you see it's much, much bigger. It reaches almost twice as high peak load, and also the absorbed energy, which is the area under the curve, is enormous compared to what you would expect these two materials to contribute with. So that's the interest, but the focus now is on the buckling of the foil. On this slide you see two pictures from a scanning electron microscope, and these are cuts across the crack plane, and you see the aluminium foil, and you see the in this case there are two polymers on each side of the aluminium foil, the LDPE. And what you can see is an indication of localization of strains at one point, and this is a cut taken ahead of the crack tip, close, not too far away from the crack tip, but still ahead of it. And in the picture to the right, the cut is taken where across the crack, and you see the aluminium foil is already broken. You can see the characteristic 1 to 2 slopes that you see at the tip that comes if you have necking, pure 45-degree shear plane type of necking, and in this case the polymer is broken on one side and not on the other. Here you see to the left the crack, exaggerated displacements and opening of the crack. The crack tip is at the origin of the X and Y coordinate system, and you can see the crack opening displacements. What you have ahead is the character of the necking, which has a maximum opening at the crack tip and then gets thinner and thinner. And to the right you see the necking type of failure of both the freestanding aluminium foil and the laminate. And the present study that I'm going to talk about is about any of these two. It doesn't matter which one, and the influence that buckling may have on this. As you see in the equation below, it's very easy to calculate the energy release from a cohesive zone like this, and it is a force. It acts as a force between the surfaces of the upper and lower parts of the specimen, and as it increases, the cross-section decreases, and if the material is, let's say, perfectly plastic, then the stress decreases linearly with the widening of the neck. On this slide you see the data for the aluminium foil, the polymer and the laminate. All of them are measured quantities, and for instance the energy release rate, critical energy release rate, the J, was taken from experiments and also proven to be very well represented by the contributions from the aluminium foil and the polymer, and when the laminate was produced and measured on it, an accuracy within 10% or even less than that. Maximum force also well predicted just by using a cohesive zone model and finite elements. This graph shows the length of the cohesive zone as a function of the remote stress and the cohesive stress. It shows the expressions both for large scale of yielding and small scale of yielding. Here the finite element result, the cross markers are compared with the exact result for a large cohesive zone, including a small one, and the small scale yielding approximation, the lower dotted curve. The first one is the dashed curve. Here's the potential energy density, which is the basis for formulating the theory around buckling. As you see, the potential energy consists of two parts, one for the bending of the plate and the other one for the work done by the in-plane stresses wherever the plate has a slope of displacements. Second equation is the variation of this potential energy with respect to any distribution of displacements. It vanishes when the material is unstable. It means that you have a distribution of displacements that doesn't affect the potential energy, and then instability is the result. To have something more than this, that is the part required for formulating a finite element theory, we also would like to have the partial differential equation, which you get easily from the expression in the middle, the variation. And it's the Euler-Lagrange formalism that gives you the derivatives, and you treat then the displacement and the displacement's derivatives, the slope and the curvature, as individual independent variables. The first equation you see here is what you end up with, and it's compactly written using the summation rule for 2 dimensions. And I hope I said that already. The comma means that you take derivative with respect to the Cartesian coordinates, 1 for x and 2 for y. This is the equation. As you see, it's linear in displacement, which means that is an eigenvalue equation, and lambda is treated as the eigenvalue here. And things are made non-dimensional here. So the coordinates are scaled with the crack length. The stresses are scaled with the nominal stress. The hat on the W doesn't actually indicate any meaningful scaling, because whatever scaling you choose, the equation will look the same, whatever you do. The eigenvalue is given in the next equation. The lambda is equal to the critical stress for buckling, crack length squared, and the thickness of the foil, and D is the plate stiffness. As you see on the top of this slide, lambda is a function of Poisson's ratio and the ratio of nominal stress to cohesive stress. Lambda approaches a function only of Poisson's ratio if the nominal stress is small. And this is what this case is. Here it is assumed to be small, and the influence of Poisson's ratio is plotted in this graph. It's usually considered to be rather small and very often not included in analysis. And here it looks like here it looks very drastic, because it goes from 1 at one end to 1.8 at the other end. But on the other hand, this covers an enormous, ridiculously almost enormous band, the entire possible region, from minus Poisson's ratio equal to minus 1 when the material becomes insharable and with infinite stiffness, and incompressible at the other end, 0.5. So normally your materials are usually placed between 0.2 and 0.4, and then the variation is not more than, well, it is some 20% or so. Not so bad as it looks when you look at the graph, though. This is the final graph of this presentation, and it's the most important one, and it shows the result from a finite element calculation done by Rick's method, and it has the horizontal axis transverse displacement, the buckling, and the vertical axis is the applied strain. And you see all the curves for all the different cohesive stresses that were the calculations were performed for goes straight up. There is an imperfection that increases, but you don't see it until you come to, let's say, 4 or 5% straining. And then it rapidly, the buckling or the displacement perpendicular to the plate increases rapidly and decreases, and then there is a snap through that is impossible to follow in practice. Also, this leads to a risk that has to be considered, that there is some imperfection or something is somewhat unwanted displacement that will make the state jump from, let's say, straining of 3 or 4 and to the bunch of curves, which also means that the load doesn't reach load of fracture. If you want to do a testing and fracture load is at 5 and 6, you may never end up there. You may have buckling first, and then you get some spooky results. The curve at the bottom is just a magnification of the top part of the graph.